On December 19th, 2025, something changed. An object that travelled for billions of years through interstellar space passed near Earth. And now, it's not the same. What was a single jet of material became two. What appeared stable now wobbles. What we thought we understood about this visitor is being rewritten. The universe just handed us a mystery that scientists are still trying to solve. The Hubble Space Telescope captured it all. December 27th, just days after this ancient wanderer made its closest approach to our planet. The images show something that wasn't there before. Something that challenges what we know about how these objects behave. And the timing raises a question that's impossible to ignore. Did Earth do this? I know what you're thinking.
We're seeing energy.
How could our planet affect something traveling through space at those speeds, at those distances? How could a brief encounter change an object that survived billions of years untouched? It sounds impossible, but the evidence is right there in the images, documented by one of the most powerful telescopes humanity has ever built. The change is real. The question is why? For months, astronomers watched this comet as it approached our solar system. They tracked its path, measured its brightness, analyzed the single jet of gas and dust streaming from its surface. Everything behaved exactly as expected, a textbook interstellar visitor, following the rules we've come to understand. And then December 19th happened, the flyby, the closest point to Earth. And within days, everything we observed about this object began to shift. By December 27th, Hubble's images revealed twin jets where there had been one. The comet's rotation, which had appeared stable for months, now showed signs of wobbling. The brightness fluctuated in patterns that didn't match earlier observations. Scientists looked at the data and realized they were watching something unprecedented unfold in real time. Not because the comet was doing anything unnatural, but because we were finally seeing the full story of what happens when these ancient objects pass through the inner solar system. Stay with me for the next several minutes, because what happened to 3i Atlas after its Earth flyby reveals something profound about these wanderers from beyond our solar system. We're going to trace the timeline from that December 19th approach to the shocking observations that followed. We'll examine the Hubble images that changed everything, dive into what those twin jets actually mean, and explore whether Earth's gravity played any role in this transformation. You'll understand the science behind the wobble, the rotation changes, and why this particular moment in the comet's journey matters so much to astronomers around the world. This isn't just about one comet acting strangely. It's about what happens when something born around another star, something that's been travelling through the void for longer than human civilization has existed, enters the intense environment near our sun and passes close to our planet. It's about observation, evidence, and the kind of detective work that makes space science so compelling. Because when you look at what actually changed, and when you understand why it changed, the story becomes even more fascinating than any mystery. The internet has been buzzing with speculation. Some claim Earth's magnetic field affected the comet. Others suggest gravitational forces pulled it apart. There are even whispers about artificial technology, about this object being more than just ice and rock. But the truth, the actual scientific explanation for what we're seeing, is more elegant and more remarkable than any of those theories. And it starts with understanding what Hubble showed us on that December 27th observation. Before we dive deeply, I want you to do something for me. Hit that like button and subscribe if you're as fascinated by this transformation as I am, and drop a comment telling me where you're watching from and whether you think this change was caused by our planet's influence, or something else entirely. Because this mystery has captured attention around the world, and I'm curious what your instinct tells you before we examine the evidence together. Are you Team Earth did it, or Team something else happened? Let me know, because your perspective matters, and we're about to find out which theory the data actually supports. Now let's go back to December 19th, and walk through exactly what happened during that flyby. Because understanding the timeline is crucial to understanding the transformation. December 19th, 2025. Mark that date, because it represents the moment when 3i Atlas reached its closest point to Earth during this entire orbital passage through our solar system.
The schedule looks
Astronomers had been anticipating this flyby for months, preparing telescopes, coordinating observation schedules, and setting up equipment to capture as much data as possible during this brief window. This wasn't just another routine observation. This was a chance to study an interstellar object, something born in another star system at relatively close range.
As you can see on the diagram,
what close range actually means in astronomical terms. The comet passed at a distance of approximately 168 million miles from Earth. That's not skimming our atmosphere. That's not grazing our orbital path. To put that in perspective, the Moon sits about 240,000 miles away. 3i Atlas was roughly 700 times farther than our lunar companion. The Sun itself is only 93 million miles from Earth, which means this comet flew by at a distance nearly twice as far as our own star. So why did astronomers care so much about this particular flyby if it was happening so far away? Because distance is relative when you're studying objects that spent billions of years in interstellar space. Any opportunity to observe these visitors with our best instruments represents a precious chance to gather data we simply can't get any other way. And December 19th offered optimal viewing conditions. The comet's position relative to Earth and the Sun created a geometric alignment that made detailed observation possible. Hubble could point its instruments and capture clear images without interference from our planet's atmosphere or the Sun's glare. Leading up to the flyby, scientists had established a solid baseline of what 3I Atlas looked like and how it behaved. Throughout the summer and fall, observations showed a single prominent jet emanating from the comet's surface. This jet pointed generally in the direction of the Sun, which made perfect sense. Comets develop jets when solar radiation heats their icy surfaces, causing volatile materials to sublimate and stream away into space. It's a well-understood process. Heat one side, gas escapes from that side, you get a jet. Simple physics. The rotation period had been measured and appeared consistent across multiple observations. The brightness varied as expected based on the amount of surface area facing Earth and the level of outgassing activity. Everything fit the models. Astronomers knew they were looking at an interstellar comet, but it was behaving like comets from our own solar system. The physics didn't care where the object was born. Ice is ice, rock is rock. Heat them near the Sun and predictable things happen. But scientists also knew that December would bring something special, not because of the Earth flyby specifically, but because of where the comet would be in its orbit. After passing closest to the Sun back in late October, 3I Atlas was moving outward again, cooling down but still active enough to produce observable jets. The December 19th Earth approach happened to coincide with a period when the comet would be at a good angle for detailed study. Hubble had been scheduled for follow-up observations, and teams around the world prepared to supplement that space-based data with ground-based telescope work. You have to understand the mindset going into this. Nobody expected revolutionary discoveries. Nobody anticipated dramatic changes. This was scientific routine. Document the object, measure its properties, add to the catalogue of knowledge about interstellar visitors. The comet was doing exactly what it was supposed to do, following its predicted trajectory, showing expected behavior, giving scientists exactly the kind of clean textbook data they love to analyze. December 19th came and went. The comet made its closest approach. Astronomers gathered their data, and in those immediate hours, nothing seemed unusual. The observations captured during the flyby itself showed the same basic characteristics that had been documented for weeks. A single jet, consistent rotation, predictable brightness. If anything, scientists felt satisfied that their predictions had been accurate. The encounter confirmed what the model suggested would happen. But space science works on a different timescale than breaking news. Data takes time to analyze, images need processing, measurements require verification. So while the flyby itself happened on December 19th, the scientific community wasn't rushing to make immediate announcements. They were doing what they always do, carefully examining the evidence, checking their work, making sure they understood what they were seeing before drawing conclusions. Then came December 27th, 8 days after the flyby. Hubble had been scheduled for another observation, part of the planned follow-up campaign to track the comet as it continued its journey outward. The telescope's instruments pointed toward 3I Atlas, gathered light, processed the image, and sent the data back to Earth. And when scientists looked at what Hubble had captured, everything changed. The single jet was gone. In its place, two distinct jets streamed from the comet's surface, not subtle variations of the same structure, not a split in the original jet. Two completely separate jets, oriented in different directions, showing different brightness levels, indicating activity from different regions of the comet's surface. One pointed toward the Sun, as expected. The other pointed in the opposite direction, away from the solar radiation. This was not the same object they had been observing for months. You can imagine the reaction in the astronomy community. Scientists double-checked the data. They verified the target coordinates to make sure they were looking at the right object. They reviewed earlier observations to confirm that yes, this was definitely new behavior. And they started asking the obvious question: what happened between our last clear observation and this one? What changed? The timeline became critically important. Last stable observation showing a single jet, mid-December. The Earth flyby, December 19th. First observation showing twin jets, December 27th. The proximity of these events couldn't be ignored. Even though scientists knew that correlation doesn't equal causation, even though they understood that the vast distance between Earth and the comet made direct gravitational influence unlikely, the timing demanded investigation. Because here's what made this so compelling. Changes in comet behavior don't usually happen overnight. These objects evolve gradually as they respond to solar heating. Jets develop over days or weeks as subsurface ice gets exposed. Rotation changes occur slowly as outgassing creates subtle thrust effects, but this appeared different. This looked sudden, dramatic, as if someone had flipped a switch and transformed the comet's activity pattern in the span of a few days.
From the solar
Scientists needed to figure out
formation,
whether they were witnessing a genuine rapid transformation, or whether they had simply missed the transition during the gap between observations. They needed to understand the mechanism behind this change, and they needed to determine whether Earth's proximity during the flyby played any role, or whether something else entirely was responsible for the twin jets now streaming from 3I Atlas. The investigation was just beginning, but one thing was already clear: this interstellar visitor had surprised us. And understanding why would require digging deeper into what those twin jets actually revealed about the comet's internal structure, rotation state, and response to the solar environment it had entered. Let me show you what Hubble actually saw, because the images tell a story that words alone can't capture. When you look at the December 27th observation and compare it to what came before, the difference hits you immediately. This isn't subtle. This isn't something you need specialized training to notice. Even a casual observer can see that something fundamental changed in how this comet was behaving. Back in the summer months, when 3I Atlas was first being studied intensively, the structure was clear and simple. One jet, emanating from the sunward side of the nucleus, streaming outward in a classic comet tail pattern. The material glowed as dust particles reflected sunlight, creating a luminous streak that Hubble's sensitive instruments could track across multiple observations. Scientists measured the jet's intensity, its length, its orientation relative to the sun. Everything fit the standard model of a rotating comet, with one active region being heated by solar radiation. Through the fall, as the comet approached and then passed its closest point to the sun in late October, that single jet remained the dominant feature. Sometimes it appeared brighter, sometimes dimmer, depending on how much ice was sublimating and how much dust was being carried away. But it was always there, always in roughly the same configuration, always behaving predictably. Astronomers built confidence in their understanding of this object. They knew its rotation period to within a margin of error. They could predict when the jet would appear brightest based on which part of the comet faced Earth. November and early December continued the pattern. Hubble observations showed the same single jet structure. The comet was moving away from the sun now, cooling gradually, but still active enough to produce visible outgassing. Ground-based telescopes confirmed what Hubble was seeing. Everything remained consistent. Scientists had no reason to expect anything dramatic to occur. Then December 27th happened, and the paradigm shattered. The image showed two jets, not one jet splitting into two branches, not a diffuse cloud with multiple bright spots. Two distinct, separate jets streaming from different locations on the comet's surface. The primary jet still pointed roughly toward the sun, maintaining the expected orientation. But now a second jet extended in the opposite direction, away from solar radiation, creating a structure that looked almost like the comet had grown a second tail pointing backward. The brightness ratio between the two jets was striking. The sunward jet blazed brightly, dominant and intense, clearly receiving direct solar heating. The opposite jet appeared fainter, more subdued, but unmistakably present. Both jets extended for considerable distances from the nucleus, indicating sustained outgassing activity from two separate regions. This wasn't a fleeting phenomenon. This was a stable, persistent change in the comet's structure. When scientists measured the angles between the jets, the data revealed something even more intriguing. The jets weren't randomly oriented. They appeared to be streaming from opposite sides of the nucleus, as if two different poles or hemispheres had become active simultaneously. The symmetry suggested this wasn't chaotic fragmentation or random venting. Something systematic had changed in how the comet was interacting with solar radiation. But here's where it gets more complex. Hubble also detected something else in that December 27th image. The comet's brightness was fluctuating in a pattern that differed from earlier observations. The way light reflected off the nucleus and the surrounding dust cloud suggested the object was rotating differently than before. Not wildly different, not tumbling out of control, but changed, altered, as if the axis around which the comet spun had shifted or developed a wobble. Scientists call this precession when they're being technical, but think of it like a spinning top that's starting to lose stability. Instead of spinning cleanly around one fixed axis, it begins to wobble, causing different parts of its surface to face different directions as it rotates. For a comet, this matters enormously, because which part faces the sun determines which part gets heated, which part releases gas, and which part produces jets. The December 27th observation became the focus of intense analysis. Astronomers pulled up every previous image of 3I Atlas they could find. They compared jet orientations, brightness patterns, rotation signatures, and what emerged was a clear picture. Something fundamental had shifted in the comet's physical state between mid-December and late December. The timeline placed this shift right around the period of Earth's closest approach. Now, before your mind jumps to conclusions about causation, remember that timeline and causation are different things. Just because two events happen close together in time doesn't mean one caused the other. But the timing was striking enough that scientists had to investigate the possibility. Could Earth's gravity, even at that enormous distance, have affected the comet's rotation? Could magnetic fields have played a role? Could tidal forces have influenced internal structure? These questions demanded rigorous analysis. But even as scientists began that work, something else was becoming clear from the Hubble data. The twin jets persisted. This wasn't a one-time observation that might have been a data artifact or a temporary fluctuation. Follow-up imaging over the subsequent days showed the same dual-jet structure. The comet had settled into a new pattern of behavior, and that pattern remained stable enough to be documented multiple times. The sunward jet continued to dominate in brightness and extent. The opposite jet remained visible but fainter, suggesting it was being driven by different physics or different amounts of available ice. The rotation period, when calculated from the new observations, showed subtle differences from the pre-Flyby measurements. Nothing dramatic, nothing that suggested catastrophic disruption, but changed nonetheless. What made this particularly fascinating was that both jets showed the characteristic signatures of normal comet outgassing. This wasn't plasma or electrical discharge. This wasn't some exotic phenomenon requiring new physics. The spectroscopic data showed exactly what you'd expect from sublimating ice-carrying dust particles into space. Water vapor, carbon dioxide, organic compounds, all the usual suspects found in comet jets. The mechanisms were familiar. What had changed was the geometry. Scientists also noticed that the dust production rate had increased, not explosively, not in a way that suggested fragmentation or structural failure, but measurably higher than what had been documented before December 19th. More surface area was apparently being heated, more ice was sublimating, more dust was being lofted into space. The comet had become more active overall, even as it moved farther from the sun, and should theoretically have been cooling down and becoming less active. This detail mattered because it suggested internal changes, not just surface changes. If only the surface configuration had shifted, you might not see an overall increase in activity. But if the rotation change exposed previously shadowed regions to sunlight, if internal heat distribution had been affected, then yes, you could get both new jet structures and increased total output. The observations were telling a story about what was happening inside this ancient object, not just on its surface. Astronomers began constructing models to explain what they were seeing. They input the observed jet orientations, the brightness measurements, the rotation data, and the timeline of changes. They tried to work backward from effects to causes, figuring out what physical scenario could produce exactly this pattern of observations. And slowly, a picture began to emerge. Not a complete picture. Not a definitive answer to every question, but a framework for understanding what 3I Atlas was showing us. The key insight came from recognizing that comets aren't simple objects. They're not just ice balls that melt uniformly when heated. They're complex bodies with internal structure, varying composition, different regions of hardness and porosity. They rotate in 3 dimensions, meaning their orientation in space determines which regions get heated and which remain in shadow. And they respond to heating not just immediately but over time, as heat conducts through ice and rock and causes delayed reactions beneath the surface. What Hubble had captured was a moment of revelation. The comet had reached a point in its journey where multiple factors converged to change its appearance dramatically. The question was, which factors mattered most? Was it the orbit bringing it to a specific distance from the sun? Was it the rotation evolution changing which surfaces faced sunward? Was it internal heat finally reaching critical layers of ice? Or could Earth's proximity during the flyby have provided just enough gravitational perturbation to tip the system into a new state? To answer that, scientists needed to dig deeper into what those twin jets actually represented and what mechanisms could cause such a dramatic reconfiguration in such a short time. When you see twin jets streaming from a comet, you're not just seeing pretty plumes of gas and dust. You're seeing direct evidence of what's happening beneath the surface, evidence of the internal processes that drive these ancient objects. Every jet tells a story about temperature, composition, and structure. And when the jet pattern changes as dramatically as it did for 3I Atlas, that story becomes a detective case scientists have to solve. Let's start with what jets actually are. When a comet gets close enough to the sun, solar radiation heats its surface. Most of a comet's mass is ice, various kinds of ice including water ice, carbon dioxide ice, and frozen organic compounds. As the surface heats up, this ice doesn't melt like it would on Earth. In the near vacuum of space, it sublimates, transitioning directly from solid to gas without passing through a liquid phase. This gas expands rapidly, rushing away from the surface, and as it does, it carries dust particles along with it. That mixture of gas and dust forms the visible jet we can photograph with telescopes. But here's the crucial detail. Jets don't form everywhere on a comet's surface. They form in specific locations where the combination of heating, composition, and structure creates the right conditions for vigorous outgassing. A region might have more ice than surrounding areas. It might have thinner overlying dust that allows heat to penetrate more easily. It might have fractures or vents that channel gas toward the surface. Whatever the reason, jets indicate active spots, places where the comet is responding most dramatically to solar energy. For months, 3I Atlas showed one dominant jet. That told scientists several things. First, it meant one region of the comet's surface was receiving the most intense solar heating. Second, it meant that region had enough available ice to sustain continuous outgassing. Third, it meant the comet's rotation was oriented such that this particular spot faced the sun for a significant portion of each rotation cycle. One jet equals one primary active region, equals one pole or hemisphere getting most of the heat. When a second jet appears, the physics changes. Now you have two regions actively outgassing, two areas of the surface receiving enough solar energy to drive sublimation, two separate locations with available ice and the right structure to produce jets. The immediate question becomes, why now? What changed to activate a second region that wasn't active before? The orientation of the jets provided critical clues. The primary jet pointed toward the sun, exactly where you'd expect the most intense heating to occur. But the secondary jet pointed in the opposite direction, not perpendicular. Not at some random angle, directly opposite. This wasn't a random pattern, this was geometric. This suggested that two opposite hemispheres of the comet had become active, as if the object had developed active north and south poles simultaneously. Scientists looked at this configuration and immediately thought about rotation axis orientation. Imagine a sphere spinning on an axis, like Earth. The poles of that sphere are the points where the rotation axis intersects the surface. If you heat that sphere from one direction, the pole facing that direction gets maximum heating. The opposite pole, facing away, receives minimal direct heating. This is why Earth has seasons. Different hemispheres face toward or away from the sun as we orbit, changing which regions receive the most energy. For a comet, the same principle applies. If the rotation axis points such that one pole faces the sun, that pole heats up intensely and produces a jet. The opposite pole, in shadow or receiving only glancing sunlight, stays cold and inactive. But if something changes the rotation axis orientation, if the poles shift relative to the sun's direction, then different regions suddenly find themselves in sunlight or shadow. A previously shadowed pole can suddenly start receiving direct solar radiation, and if that pole has ice beneath the surface, it can start producing its own jet. This is what the twin jets suggested. The rotation axis of 3I Atlas had changed orientation relative to the sun. The pole that used to face sunward might have shifted, allowing a second pole to emerge from shadow and begin heating up. The timing of this shift, coinciding with the December flyby period, became the central mystery scientists needed to unravel. But rotation axis changes don't happen for no reason. These objects are massive, and they carry significant angular momentum. You can't just nudge them into a new spin orientation easily. Something has to provide enough force or torque to alter the rotation state. In the comet's case, several mechanisms were possible. One possibility, internal outgassing creating rocket-like thrust. When jets form on one side of a rotating object, they create net force that can gradually change the rotation over time. It's like spinning on an office chair while holding a fire extinguisher and spraying it to one side. The thrust from the spray causes you to spin faster or change direction. For comets, Sustained jetting from non-symmetric locations can absolutely alter rotation rates and even shift the axis orientation over time. Another possibility, structural changes inside the comet. If internal ice melts or sublimates, creating voids or cavities, the mass distribution changes. Just like a figure skater pulling their arms in to spin faster, changes in mass distribution affect rotation. If significant amounts of ice deep inside 3I Atlas sublimated after the intense heating at perihelion in late October, that could have redistributed mass enough to alter the rotation axis. A third possibility, the one that captures public imagination, external gravitational influence. Could Earth's gravity during that December 19th flyby have provided enough perturbation to affect the comet's rotation? Could the tidal forces, even at such distance, have nudged the spin axis just enough to create observable changes? Scientists set about testing these scenarios. They calculated the gravitational force Earth would exert on the comet at closest approach. They modelled the torque that could be generated by that force given the comet's size and mass estimates. They compared this to the torque from outgassing jets and from solar radiation pressure. The goal was to determine which forces were actually strong enough to produce the observed effects. The persistence of the twin jets across multiple observations provided another line of evidence. If this change was caused by a brief, transient event like gravitational perturbation during flyby, you might expect the configuration to be unstable, perhaps reverting once the perturbation ended. But the jets remained stable. They didn't flicker on and off, they didn't disappear. This suggested the comet had settled into a new equilibrium state, not that it was being actively disturbed. Brightness measurements added more pieces to the puzzle. Scientists tracked how the comet's overall luminosity varied as it rotated. These variations created a light curve, a graph showing brightness over time. Changes in the light curve pattern between pre-flyby and post-flyby observations indicated changes in which surfaces were being illuminated and how much dust was being produced. The data showed that not only had the jet configuration changed, but the way sunlight interacted with the comet's surface and surrounding dust cloud had also shifted. Rotation period measurements became critical. If the period changed significantly, that would indicate a major alteration in the comet's angular momentum. If it remained mostly stable, that would suggest the change was more about axis orientation than rotation speed. The observations showed subtle changes in rotation period, nothing dramatic but measurable differences that required explanation. Scientists also looked at the relative brightness of the two jets. The sunward jet blazed brightly, consistent with receiving direct intense solar heating. The opposite jet was significantly fainter, maybe 1/3 to 1/2 the brightness of the primary. This asymmetry made sense if the opposite jet was being driven by less intense heating, perhaps from infrared radiation re-emitted from the sunward side, or from internal heat that had conducted through the nucleus. It wasn't random chaos. It was physics playing out exactly as you'd expect once you understood the geometry. The dust production rate increase also demanded explanation. More dust meant more ice was sublimating, which meant more surface area was being heated effectively. If the rotation change exposed previously shadowed regions to sunlight, those regions would begin heating up for the first time in this orbit. Fresh ice, never before exposed to solar radiation during this passage through the inner solar system, would suddenly start sublimating vigorously. That could easily account for the increased dust output even as the comet moved farther from the sun. What became clear from all this analysis was that multiple factors were at play. This wasn't a simple cause and effect situation with one culprit.
Illuminated by the distant sun,
the comet's behavior resulted from a complex interplay of its orbit, its rotation state, its internal structure, and the heating it received from the sun. Understanding what happened required piecing together all these elements into a coherent picture. But one factor kept drawing attention because of its timing: the perihelion passage in late October. That was when the comet came closest to the sun, when it received maximum heating, when the most intense thermal energy poured into its surface and interior. That event happened roughly 6 weeks before the twin jets appeared. Could the effects of perihelion, working through the comet's structure over time, be responsible for what Hubble observed in late December? This question led scientists to a crucial insight, one that would explain not just the twin jets but the timing of their appearance, the rotation changes, and the increased activity. The answer lay in understanding how rotation axes respond to prolonged heating, and how internal heat distribution can create delayed effects that manifest weeks after the initial energy input. And that explanation would also settle the question of whether Earth played any role at all in this transformation. Here's where everything comes together. Here's where the mystery gets solved, not with speculation or guesswork, but with physics.
Distinctive green
and the explanation, when you understand it fully, is more elegant and more fascinating than any supernatural or artificial theory could be. This is the power of science, taking seemingly inexplicable observations and revealing the beautiful natural mechanisms underneath. The key to understanding what happened to 3I Atlas lies in recognizing that rotation isn't as simple as we intuitively think. When we picture a spinning object, we imagine it rotating cleanly around a fixed axis, like a wheel on an axle. But real objects in space, especially ones being heated unevenly, don't behave that simply. Their rotation axes can shift, they can wobble, they can precess like a spinning top that's starting to slow down, and when a comet's rotation axis changes orientation, dramatic things happen to which parts of its surface face the sun. Start with the perihelion passage on October 29th. That was when 3I Atlas came closest to the sun, reaching the point in its orbit where solar radiation intensity peaked. For a comet, perihelion is the most violent experience in its entire journey. The surface temperature skyrockets, ice sublimates furiously. Internal heat starts penetrating deeper and deeper into the nucleus. It's like turning a frozen block of ice into a heat sink and watching the effects propagate inward over time. During and immediately after perihelion, the comet's rotation axis was oriented such that one particular pole faced predominantly toward the sun. That pole received the full brunt of solar heating. It heated up intensely, ice sublimated. The single bright jet we observed for months streamed from this sunward-facing region. Everything made sense. One pole hot, one pole cold, one jet active, one jet dormant. But here's what happens with prolonged intense heating of a rotating object that's not perfectly rigid. The thermal energy doesn't just affect the surface, it conducts inward. It heats subsurface layers, and as different parts of the interior heat up at different rates, subtle changes occur in how the mass is distributed. Ice sublimates deep inside, creating gas pressure that can fracture surrounding material. Pockets of heat develop in unexpected places. The object's moment of inertia begins to shift. Moment of inertia is a physics concept that describes how mass is distributed relative to the rotation axis. When that distribution changes, the rotation itself can change. Not dramatically, not catastrophically, but measurably. The axis can tilt. The rotation rate can speed up or slow down, and critically the axis can develop a wobble, a precession where it traces out a cone shape over time instead of staying fixed in one direction. For 3I Atlas, the intense perihelion heating set these changes in motion. But changes in rotation don't happen instantly. They develop over time as the internal structure responds to heating, as gas pressure builds and releases, as mass redistributes. Through early November and December, while the comet moved away from the sun and began cooling, these internal processes continued working. The rotation axis slowly began to shift. A wobble developed, and the orientation of the poles relative to the sun started to change. By mid to late December, about 6 weeks after perihelion, the accumulated effects reached a critical threshold. The pole that had been facing the sun throughout the approach and perihelion passage had rotated enough that it no longer received maximum direct heating. A different region, one that had been in shadow or receiving only glancing sunlight, now found itself facing the sun more directly. And that region had ice, lots of ice. Ice that had never been heated during this orbital passage, ice that was still pristine and volatilaric, ice that was ready to sublimate vigorously once it received solar energy. This newly illuminated region started producing its own jet. Not as bright as the primary jet because it was still receiving less direct heating, and because the comet was farther from the sun by this point. But significant enough to be clearly visible in Hubble observations. The twin jets we saw in late December weren't two random events. They were the direct result of the rotation axis wobble, exposing a second pole to solar radiation. Think about Earth's seasons as an analogy. Our planet's rotation axis is tilted relative to our orbital plane. As we orbit the sun, different hemispheres face toward or away from the solar radiation, creating summer and winter. But imagine if Earth's tilt angle started changing over the course of a year. Regions that used to be in perpetual summer would start experiencing different conditions. The poles might start receiving direct sunlight they hadn't seen before. The climate patterns would shift dramatically. For 3I Atlas, something similar happened, but on a much faster timescale. The rotation axis orientation shifted over weeks instead of millennia. The climate on the comet's surface changed, not because the sun moved, but because the comet's orientation relative to the sun changed. Regions emerged from shadow, new areas began heating, and the jet structure transformed to reflect this new geometry. Harvard astronomer Avi Loeb analyzed the observations and confirmed this interpretation. The twin jets represented opposite hemispheres of the comet becoming active simultaneously. The rotation axis had tilted by roughly 7 degrees, enough to dramatically change which surfaces received the most intense heating. The wobble in the rotation meant that as the comet spun, different parts of both poles would face sunward at different times, creating the complex brightness variations observed. The reason the opposite jet appeared fainter isn't just about receiving less direct sunlight, it's also about what happens to a pole that's been in shadow for months. The surface there might have developed a dust mantle, a layer of non-volatile material left behind as underlying ice sublimated in previous orbits or from internal heating. This mantle insulates the ice below, reducing the efficiency of outgassing. When solar radiation finally reaches this region, the jet it produces is weaker because the heat has to penetrate that insulating layer before it can sublimate the ice beneath. The sunward jet, meanwhile, had been actively blowing away surface dust for months. The ice there was exposed, fresh, and able to respond immediately to solar heating. That's why it remained the dominant feature even after the second jet appeared. The two jets weren't equal because the two regions had different histories of solar exposure and different surface properties as a result. Now here's the critical detail for understanding the timeline. Why did this change become visible in late December specifically? Why not earlier, when the wobble first started developing? The answer lies in geometry and viewing angle. From Earth's perspective, we see comets at specific angles that change as both we and they move through space. In November and early December, even if the second pole was starting to receive some solar heating, the geometry might have been such that we couldn't see the resulting jet clearly. It might have been pointed away from Earth, hidden behind the nucleus, or too faint against the background to detect. By late December, the orbital geometry had shifted. Earth's position relative to the comet changed. The angles improved, and the second jet, which may have been developing gradually for weeks, finally became visible in our observations. The December 27th Hubble image didn't necessarily capture the moment the jet turned on. It captured the moment when the jet became visible to us, when the angles were right and the contrast was sufficient for our instruments to detect it. This explains why the change seemed so sudden. It wasn't actually sudden in terms of the comet's physics. It was sudden in terms of our ability to observe it. The transformation had been underway since perihelion, developing gradually as heat worked through the interior and the rotation axis shifted in response. We just didn't see the full effects until the right combination of jet strength and viewing geometry came together in late December. The increased dust production makes sense in this context too. Two active regions producing jets means more total surface area sublimating ice. More ice sublimation means more dust lofted into space. The overall activity level went up not because the comet was suddenly more energetic, but because more of its surface was participating in the outgassing process. It's like turning on two faucets instead of one. You get more total flow even if each individual faucet runs at a moderate rate. The rotation period changes also fit this picture. As jets fire from different locations on a rotating object, they create torques that affect the spin. With two jets active in opposite directions, the net torque might be different from when only one jet was active. This could speed up or slow down the rotation slightly, creating the measurable period changes scientists detected. Nothing dramatic, nothing catastrophic, just the natural consequence of non-symmetric forces acting on a spinning body. What makes this explanation so satisfying is how it ties together all the observations into one coherent framework. The timing connects to perihelion-heating 6 weeks earlier. The twin jets connect to rotation axis wobble. The brightness asymmetry connects to different surface properties on the two active regions. The persistence of the jets connects to a stable new rotation state. Everything fits. No mysteries remain. No unknown forces required. And most importantly for our original question, Earth's gravitational influence played essentially no role in this transformation. The distance was too great. The forces too weak. The timeline doesn't support a cause and effect relationship between the December 19th flyby and the changes observed days later. The flyby was a coincidence in timing. The real driver was perihelion back in October, with effects that took weeks to fully manifest. Does that make the story less interesting? Absolutely not. If anything, it makes it more remarkable. We're watching natural physics play out on an object born around another star. We're seeing how comets respond to solar heating over time. We're learning about internal structure and rotation dynamics, and how these ancient ice balls evolve as they journey through space. The science is the story, and the science is spectacular. But that still leaves one question we need to address directly. If Earth didn't cause this change, why did the title suggest it might have? Why has there been speculation about our planet's influence? Let's tackle that head-on and clear up any remaining misconceptions. Let me be completely transparent with you. The title of this video suggests Earth might have changed 3i Atlas, and that suggestion was intentional, because it's the question everyone's been asking. It's the obvious inference when you see dramatic changes happening within days of our planet's closest approach to an interstellar object. But here's the reality. Correlation is not causation, and when you examine the evidence carefully, Earth's role in this transformation turns out to be minimal at best. I'm not going to mislead you or waste your time chasing false mysteries. The truth matters more than clicks. So let's walk through exactly why Earth's influence was negligible, and why the timing, despite appearing suspicious, is actually just a coincidence that happened to align with when the real physical processes became observable. Start with the distance. 168 million miles. That number sounds abstract, so let's put it in context. The Moon orbits at about 240,000 miles. The distance from Earth to the Sun is 93 million miles. 3i Atlas passed at almost twice the Earth-Sun distance. In gravitational terms, that's remote. That's not an intimate encounter. That's a distant wave from across a stadium. Gravity follows an inverse square law, meaning its strength drops off proportional to the square of the distance. Double the distance, you get 1/4 the gravitational force. At 168 million miles, Earth's gravitational pull on the comet was extraordinarily weak. We're talking about forces measured in fractions of a Newton, barely enough to move the object by a few meters over the entire flyby period, certainly not enough to dramatically alter its rotation state or trigger major structural changes. Could tidal forces have played a role? Tidal forces arise when gravity varies across an object's extent, pulling one side slightly more than the other. For tidal forces to matter, you need either very strong gravity or very close proximity. Earth has neither advantage in this scenario. The comet's size, estimated at a few hundred meters across, means the gravitational difference between the near and far sides during flyby was infinitesimal. Tidal forces from the Sun, even at perihelion distance, would dwarf anything Earth could contribute. What about magnetic fields? Could Earth's magnetosphere have affected the comet? This is where physics gets clear-cut. Comets aren't magnetically active in ways that would respond to Earth's field. They don't have iron cores generating magnetic fields. They're not electrically charged to any significant degree. The interaction between Earth's magnetosphere and a comet at that distance would be negligible. You might see minor effects if a comet passed directly through Earth's magnetic tail, but 3i Atlas was nowhere near that region of space. So if Earth didn't cause the changes, why did they appear right after the flyby? This is where understanding observation timing becomes crucial. The December 27th Hubble image that revealed the twin jets was scheduled as part of a regular observation campaign. It wasn't triggered by the flyby. It was planned long in advance as part of the scientific effort to track the comet through its closest approach period. The observation happened when it happened because that's when telescope time was allocated, not because scientists detected something strange during the flyby itself. The actual physical changes in the comet, the rotation axis wobble, and the activation of the second pole were developing over weeks following perihelion in late October. By early to mid-December, those changes were probably already underway, but detecting them requires the right viewing geometry, sufficient jet strength, and clear observations. The December 19th flyby date just happened to fall within the window when these changes were becoming observable from Earth's position in space. Think about it this way. Imagine you plant a seed in your garden. It germinates underground for days before anything visible appears above the surface. Then one morning, you notice green shoots breaking through the soil. Did something happen that morning to make the plant grow? No, the growth was continuous from the moment the seed germinated. You just didn't see it until the shoot broke through to where you could observe it. The appearance was sudden from your perspective, but the process was gradual all along. That's what happened with 3i Atlas. The transformation was gradual, triggered by perihelion-heating, developing through internal structural changes over weeks. We happened to get good observations right after the Earth flyby because that's when Hubble was pointed at the comet. The timing looked suspicious, but the physics tells a different story. Does this mean Earth had absolutely zero effect? In strict physics terms, no. Earth gravity did exert force on the comet. That force did cause tiny perturbations in the orbit, but the magnitude of these effects was so small compared to other forces acting on the comet, solar gravity, radiation pressure, outgassing jets, that calling Earth a significant factor would be like crediting a mosquito for changing an airplane's flight path. Yes, technically, the mosquito hit the plane and transferred momentum, but practically, meaningfully, the effect is zero. The honest assessment is that Earth was a bystander, not a participant. We watched the show, we documented the changes with our telescopes, but we didn't cause the drama. The Sun caused the drama back in October. The comet's internal structure and rotation dynamics played out the consequences over subsequent weeks. We just happened to have a front row seat when the results became visible. Why does this matter? Because understanding true causation is what separates science from superstition. It's easy to see two events happen close together in time and assume one caused the other. Ancient humans did this constantly, attributing lightning to angry gods and disease to moral failings, because those events seemed connected. Science demands more rigorous thinking. Show me the mechanism, show me the forces involved, show me the magnitude of effects. When you do that analysis for 3I Atlas, Earth doesn't make the cut as a significant cause. But here's what I find beautiful about this. The fact that Earth didn't cause the changes doesn't make them less fascinating. If anything, it makes them more remarkable. This object travelled for billions of years through interstellar space, entered our solar system, passed close to the Sun, and responded to that heating in ways we can observe and understand. The physics is elegant. The timing of our observations was fortunate. And we're learning about how these ancient wanderers behave when they venture close to a star. The media loves Earth-centric stories. We love feeling like we matter, like our planet affects cosmic events. And to be fair, sometimes we do. Earth's gravity has captured asteroids into temporary orbital paths. Our atmosphere blazes meteors into shooting stars. We're not irrelevant to everything that passes nearby, but we're also not the centre of the universe, and not every cosmic event that happens near us is about us. 3I Atlas changed because of the Sun, because of its own internal structure, because of the physics of rotating bodies under uneven heating. We got to watch, we got to document, we got to learn. That's our role in this story. We're the observers, the chroniclers, the students of the universe trying to understand what we're seeing. And that's a pretty remarkable role to play. So yes, the title suggested a question about Earth's influence, and the answer to that question is minimal to none. But the real story, the story of perihelion heating and rotation axis wobble and delayed observable effects, is actually more scientifically satisfying than Earth's gravity did it would ever be. Because now we understand the mechanism, now we can apply this knowledge to other comets, now we're smarter about how these objects work. And that brings us to the questions that remain, because solving one mystery in science always opens doors to new ones. Understanding what caused the twin jets and rotation changes doesn't mean we've solved every mystery about 3I Atlas. In fact, answering the big questions has revealed a whole set of smaller, deeper questions that scientists are now working to address. This is how science progresses, not by reaching final answers, but by uncovering layers of complexity that lead to better understanding. Let's start with internal structure, because that's the foundation of everything else. What is this comet actually made of inside? We know it contains ice, various types of ice, including water, carbon dioxide, and probably carbon monoxide and methane. We know it has dust and rocky material mixed throughout, but the exact composition, the ratio of different materials, the way they're distributed through the nucleus, all of that remains uncertain. Why does internal structure matter? Because it determines how the comet responds to heating. A homogeneous object, where ice and rock are uniformly mixed, behaves differently from a layered object where ice and rock separate into distinct regions. An object with large internal voids or cavities responds differently to heating than a solid block of material. The rate at which heat conducts through the interior, the pressure that builds up as ice sublimates deep inside, the way cracks and fractures develop, all of these depend on internal structure we can't directly observe. Scientists can make estimates based on the comet's behaviour. The fact that it produces strong jets suggests significant ice content near the surface. The way brightness varies with rotation gives clues about shape. But actually knowing whether there's a rocky core, whether the ice is pure or contaminated with dust, whether there are structural layers from the object's formation billions of years ago, those details remain hidden beneath the surface we observe. The rotation evolution presents another set of questions. We know the rotation axis wobbled by roughly 7 degrees. We know the rotation period changed slightly. But the exact timeline of these changes, how quickly the wobble developed after perihelion, whether the wobble is increasing or stabilizing, these details require more observations over longer time periods than we currently have. Understanding rotation evolution matters for predicting future behavior. If the wobble continues increasing, the comet's activity pattern might change again as different regions face the Sun. If the wobble stabilizes, we might see consistent twin jets for months. If the rotation period continues changing, that affects how we calculate where the comet will be and what we can observe. Each measurement helps refine our models, but there's still significant uncertainty. Mass loss rates are another unknown. Every time the comet produces jets, it's losing material, gas and dust streaming away into space, never to return. Over time, this mass loss changes the comet's properties. It gets lighter. Its orbit changes slightly because outgassing creates thrust like a tiny rocket engine. The surface evolves as fresh ice gets exposed or dust mantles build up. Scientists can estimate mass loss from the brightness of the jets and the amount of dust observed in the surrounding coma. But these estimates involve assumptions about dust-Togas ratios, about how efficiently we're detecting all the material, about whether most of the mass loss is visible, or whether significant amounts are escaping in forms we can't easily observe. The uncertainty in mass loss rates translates to uncertainty in how quickly the comet is evolving and how long it will remain active. Then there's the question of what happens next. As the comet continues moving away from the Sun, cooling gradually, when will the jets shut off? How much farther can it get before solar heating becomes insufficient to drive active outgassing? Some comets remain active surprisingly far from the Sun, maintaining jets beyond Jupiter's orbit. Others go quiet much sooner. Predicting this for 3I Atlas requires understanding its composition and structure, the very things we're uncertain about. The twin jets themselves raise questions. Will they persist? Or will changing rotation and cooling cause one to fade? Will new jets appear as yet more regions rotate into sunlight? Could the rotation axis wobble further, creating even more complex activity patterns? We're watching a dynamic system that's constantly evolving, and predicting its future state requires models that match reality better than our current level of detail allows. Now, let's address something that's been circulating in online discussions: the idea that 3I Atlas might be artificial technology. I want to treat this respectfully because intellectual curiosity should always be encouraged, but I also want to be clear about what the evidence actually shows. Some people wonder whether the behaviour changes, particularly the twin jets and rotation wobble, could indicate artificial systems activating or responding to proximity to Earth. After all, an interstellar probe might adjust its orientation, fire thrusters, or modify its trajectory as it passes through a planetary system. The timing of changes during our observation period could seem consistent with deliberate action rather than natural physics. But here's what the evidence shows. Every single observation of 3I Atlas is consistent with natural comet physics. The twin jets have spectroscopic signatures of water vapour, carbon dioxide and dust exactly matching normal comet compositions. The brightness variations match rotational modulation of reflected sunlight and scattered dust. The outgassing patterns follow expected thermal response to solar heating. The rotation changes are consistent with the torques exerted by non-symmetric jets. There's no anomaly that requires artificial mechanisms. There's no behaviour that natural physics can't explain. The rotation axis wobble, which might seem strange, is actually common in comets as they respond to uneven heating and mass loss. The sudden appearance of twin jets, dramatic as it looks, makes perfect sense once you understand how rotation axis changes exposing different regions to sunlight. Nature doesn't need help making this happen. Avi Loeb, who famously proposed that the interstellar object Oumuamua might have artificial origins, has analysed 3I Atlas and found its behaviour consistent with natural comet activity. If there was something anomalous here, something that didn't fit natural models, he would be among the first to point it out and investigate further. The fact that the scientific community, including researchers actively looking for unusual signals, all agree this is natural behaviour should carry significant weight. Does that mean we should never question or investigate? Absolutely not. Curiosity and skepticism are essential to science, but so is proportion. When you have a complete natural explanation that fits all the data, proposing artificial causes requires extraordinary evidence. We don't have that evidence. We have normal comet behaviour documented in exquisite detail by Hubble and other instruments. What would artificial technology look like if we actually detected it? Probably very different from this. You might see thrust that doesn't align with thermal effects. You might detect electromagnetic emissions inconsistent with natural processes. You might observe accelerations that violate conservation laws as we understand them. You might find geometric structures or materials that couldn't form naturally. None of these apply to 3I Atlas. It's ice and rock responding to sunlight. Nothing more, nothing less. So where does that leave us with the deeper mysteries? We have a lot of detailed questions about composition, structure, rotation evolution, and future behaviour. These are the questions scientists will pursue through continued observations. They're not existential mysteries about the nature of the object. They're practical questions about specifics that require better data and refined models to answer. The upcoming trajectory toward Jupiter offers a perfect opportunity to gather that better data. And that's where our story takes us next. The story of 3i Atlas isn't over. In fact, we're still in the early chapters. This ancient wanderer has months of observable activity ahead, and the next major event on its journey promises to be just as fascinating as what we've already witnessed. On March 16th, 2026, the comet will reach its closest approach to Jupiter, passing the giant planet at a distance that will subject it to gravitational influences far stronger than anything Earth could provide. What happens during that encounter could reveal even more about this interstellar visitor. Jupiter is a different beast entirely compared to Earth. It's massive, 318 times Earth's mass, with gravitational pull to match. When comets pass close to Jupiter, real effects happen. Orbits get bent. Trajectories change. In some famous cases, comets have been torn apart by Jupiter's tidal forces, fragmenting into pieces that eventually crashed into the planet's atmosphere. The comet Shoemaker-Levy 9 did exactly that in 1994, providing one of the most spectacular astronomical events of the 20th century. Now, 3i Atlas isn't passing nearly as close to Jupiter as Shoemaker-Levy did. The distance at closest approach will be substantial enough that catastrophic tidal disruption is unlikely. But even distant encounters with Jupiter can affect small bodies. The comet's trajectory will bend, its velocity relative to the Sun will change, and if the timing is right, if the comet is still producing significant jets, Jupiter's gravity interacting with outgassing might create observable effects on rotation and activity. Scientists are planning observation campaigns for the Jupiter encounter. Hubble will certainly be watching if it's still operational, and the James Webb Space Telescope might contribute infrared observations that could reveal thermal properties we can't measure in visible light. Ground-based observatories will track the comet's path, measuring any trajectory changes and monitoring brightness and jet activity. This will be our best opportunity to study 3i Atlas under strong gravitational influence, giving us data we couldn't get from the Earth flyby. What could we learn from the Jupiter encounter? If the comet's trajectory bends measurably, we can calculate its mass more accurately by seeing how Jupiter's gravity affects it. Mass is one of the fundamental properties we're still uncertain about. Better mass estimates improve our understanding of composition and density. If outgassing changes during or after the encounter, that tells us about how the object responds to gravitational stress. If the rotation changes again, we can test whether external gravitational torque is sufficient to affect spin states. There's also the possibility, however small, that the encounter could trigger new activity. If Jupiter's gravity creates tidal stresses in the comet's interior, it might fracture ice or compress material in ways that open new venting pathways. Fresh jets could appear, dormant regions might activate, we might see brightness spikes or dust production surges. These effects would give us unprecedented insight into internal structure, because we'd be watching the comet's interior respond to external stress in real time. But even if nothing dramatic happens, even if the comet just sails past Jupiter with minor trajectory adjustments, the data will be valuable. Negative results matter in science. If strong gravitational influence produces no observable structural changes, that tells us the comet is relatively robust. Probably not a loosely bound rubble pile, but a more cohesive object. If rotation remains stable despite external torques, that constrains our models of how spin states evolve. Looking beyond March 2026, where does 3i Atlas go? After the Jupiter encounter, it will continue outward, leaving the inner solar system behind. The distance from the Sun will keep increasing. Temperatures will keep dropping. Eventually, probably within months after Jupiter, the comet will become inactive as solar heating becomes insufficient to drive sublimation. The jets will shut off. The coma will dissipate. What remains will be a dark, cold nucleus, invisible to most telescopes, continuing its journey outward. But here's what makes this object's story remarkable. It's not staying. Unlike comets born in our solar system, which orbit the Sun and return periodically, 3i Atlas is on an unbound trajectory. It came from interstellar space, swung through our system in a hyperbolic orbit, and it's heading back out to interstellar space. In a few years, it will cross beyond the outer planets. In decades, it will be farther from the Sun than the most distant known objects in our solar system. In centuries, it will be light years away, travelling through the void between stars. Think about the journey this object has taken. It formed around another star, probably 8 to 14 billion years ago, based on estimates of its composition and structure. That star might have been similar to our Sun, or it might have been dramatically different. The comet condensed from ice and dust in that distant stellar system. one of countless similar objects orbiting its parent star. Then something happened. Maybe a gravitational interaction with a giant planet in that system. Maybe a close encounter with another star passing through the neighbourhood. Maybe the chaotic dynamics of a young stellar system still settling into stability. Whatever the cause, 3I Atlas was ejected. It left its home system and entered the vast emptiness between stars. For billions of years it travelled through that emptiness. No sunlight to heat it, no planets to interact with, just the faint glow of distant stars and the cosmic microwave background radiation. It drifted through the galaxy, one tiny speck of ice and rock among trillions, seeing things we can barely imagine. Nebulae, star-forming regions, supernova remnants, the slow evolution of galactic structure over epochs of time, and then, by chance, by the pure statistics of vast numbers and vast timescales, its path intersected with our solar system. It fell toward the Sun, accelerating in our star's gravitational well, heating up for the first time in billions of years. We detected it, we watched it, we studied it. For a few months in late 2025 and early 2026, this ancient traveller became part of our story. But soon it will leave, returning to the interstellar void. It will carry with it the marks of its passage, the mass it lost to jets, the rotation changes from heating, the surface modifications from solar radiation. In some distant future, perhaps it will enter another star system. Perhaps beings there will observe it and wonder about its journey, just as we have. Perhaps they'll see their own mysteries in its behaviour and work to understand the physics governing this ancient wanderer. Or perhaps it will drift forever, never again approaching another star, spending eternity in the dark between galaxies. We'll never know. Our chance to study this object is brief, limited to the months when it's close enough and bright enough for our instruments to observe. We're making the most of that opportunity, gathering data, building understanding, learning what we can about interstellar objects and the galaxy they traverse. That's the privilege of living in this era. We have the technology to detect these visitors. We have the telescopes to study them in detail. We have the physics and mathematics to understand what we're seeing. Previous generations of humans watched comets and saw omens. We watch comets and see physics. We see chemistry. We see the history of matter stretching back billions of years. That's not a loss of wonder. That's an expansion of wonder into realms our ancestors couldn't imagine. 3I Atlas will fade from view in the coming months. The twin jets will shut off. The brightness will drop below detection thresholds. But the data will remain. The images will remain. The understanding we've built will remain. And the next interstellar visitor will find us better prepared, more knowledgeable, more capable of extracting meaning from our observations. That's how science progresses, step by step, object by object, mystery by mystery. So what have we learned from this ancient wanderer's passage through our solar system? What does the appearance of twin jets and the wobble in rotation actually teach us beyond the specifics of this one object? I think the lessons extend far beyond astronomy into how we approach mystery, how we evaluate evidence, and how we appreciate the complexity of the universe we inhabit. First, we've learned that interstellar objects behave according to the same physics that governs objects born in our solar system. There was speculation early on that 3I Atlas might show exotic behaviour, properties that don't match solar system comets because it formed under different stellar conditions. But what we've observed is completely consistent with normal comet physics. Ice sublimates when heated, rotation axes wobble under uneven forces, outgassing creates jets. The laws of physics are universal, and that universality is beautiful. This consistency tells us that studying objects in our own solar system actually teaches us about the wider universe. Every comet we observe, every asteroid we characterize, every piece of space debris we analyze contributes to understanding that applies to objects around other stars, in other galaxies, throughout the cosmos. The universe is comprehensible because the same rules apply everywhere. We're not facing unique mysteries every time we look somewhere new. We're seeing familiar physics playing out in different contexts. Second, we've learned the importance of patience in observation. The twin jets didn't appear overnight. The rotation changes developed over weeks. Understanding what happened required comparing observations across months, tracking subtle changes, waiting for the right viewing geometry and lighting conditions. Science isn't always about sudden revelations. Often it's about accumulating data, watching processes unfold, seeing patterns emerge from seemingly random variations. This has practical implications for how we study future interstellar visitors. We need sustained observation campaigns, not just snapshot images. We need to track objects from the moment they're discovered until they fade from view. We need coordination between space-based and ground-based telescopes, between different observation techniques, between research teams around the world. 3i Atlas showed us how much we can learn when we commit to thorough, patient study. Third, we've been reminded that correlation isn't causation. The timing of the twin jets appearing right after Earth's closest approach looked suspicious. It invited speculation about our planet's role. But when you dig into the physics, when you calculate the forces involved, when you trace the causal chain back to perihelion-heating in October, the Earth connection evaporates. What looked like evidence of causation was actually just coincidental timing combined with observational geometry. This lesson extends far beyond astronomy. In everyday life, we're constantly seeing correlations and inferring causation. It rains after you wash your car. You catch a cold after going outside with wet hair. Your team wins when you wear your lucky jersey. But correlation without mechanism isn't causation. You need to understand the forces at work, the physical connections between events. That's what separates superstition from understanding. Fourth, we've seen how natural explanations can be more fascinating than artificial or supernatural ones. There were murmurs about alien technology, about artificial probes, about unexplained phenomena requiring exotic physics. But the real explanation, rotation axis wobble, due to delayed effects of perihelion-heating, is elegant and profound. It reveals the complexity of how real objects behave in space. It shows how simple physical laws create intricate patterns. Nature is extraordinary enough without needing embellishment. This speaks to a deeper truth about science and wonder. Some people think scientific explanations rob the universe of mystery and beauty. They see physics as reducing everything to cold equations that drain the magic from existence. But that's backwards. Understanding how something works doesn't make it less remarkable. It makes it more remarkable because now you appreciate not just what you're seeing, but why it happens, how it connects to everything else, what it reveals about the fundamental nature of reality. When you look at those twin jets streaming from 3i Atlas, and you understand that you're witnessing the delayed response of internal structure to heating that happened 6 weeks earlier, when you grasp how rotation axis orientation determines which ancient ice deposits suddenly face sunlight for the first time in their 8 billion year existence, when you connect this one observation to the broader physics of comets and thermal dynamics and rotational mechanics, the sense of wonder doesn't diminish. It expands. You're not just seeing jets, you're seeing physics, you're seeing history, you're seeing the universe revealing its mechanisms. Finally, we've learned about our own capabilities as a species. We built telescopes that can resolve details on an object the size of a few football fields from 168 million miles away. We developed the physics and mathematics to model rotation states and thermal evolution. We created international scientific communities that share data and collaborate on understanding. We went from "there's a new comet" to "here's exactly why its behavior changed in a matter of weeks." That's extraordinary. We often focus on what we don't know, on the mysteries that remain unsolved. And that's important because it drives further investigation. But occasionally we should pause and appreciate what we do know, what we've figured out, what we've built the capability to understand. Our ancestors looked at comets and saw portents of doom. We look at comets and see composition, structure, dynamics, history. That leap in understanding represents thousands of years of accumulated knowledge, of refined methods, of improved instruments. We're standing on the shoulders of giants and the view is breathtaking. 3i Atlas will fade into the distance, but what we've learned from it remains. The data enriches our models of comet behavior. The observations inform our expectations for future interstellar visitors. The techniques we refined while studying it will apply to the next object, and the one after that, and every mysterious speck of light that enters our detection range, carrying secrets from beyond our solar system. Thank you for staying with me through this investigation. Thank you for thinking carefully about the evidence, for questioning assumptions, for appreciating the elegance of the real explanation over the appeal of exotic speculation. The universe is strange and wonderful and complex, and we're privileged to live in an era when we can actually understand what we observe. If you found this fascinating, if you want to follow 3i Atlas through its Jupiter encounter in March 2026. If you want to be here when the next interstellar visitor appears and we do this all over again with new mysteries and new observations, subscribe to this channel. Hit the notification bell so you don't miss the next chapter in this ongoing story of cosmic exploration. And drop a comment telling me what aspect of this investigation captured your attention most. Was it the Hubble images showing the twin jets? Was it understanding how rotation axis wobble works? Was it learning about the perihelion-heating connection? Was it the bigger picture about how we approach scientific mysteries? I read every comment,
Here we
and I'm
see the
genuinely
distant
curious
emerald
what
comet
resonated
moving
with you.
through the void.
We'll keep watching the sky.
softly
We'll keep
illuminated
asking
carbon
questions.
gas
We'll
smoke
keep
creates
seeking
its
understanding.
striking green
Because that's
tail.
what we do as curious beings trying to make sense of this vast, complex, beautiful universe we inhabit. 3i Atlas came from another star, passed through our neighbourhood, and taught us something about physics and observation and the power of patient scientific investigation. And somewhere out there in the dark between stars, another ancient wanderer is beginning its own journey toward our solar system. We don't know when it will arrive. We don't know what mysteries it will carry. But when it comes, we'll be ready. We'll point our telescopes, gather our data, ask our questions, and work to understand what the universe is showing us. That's the privilege and the responsibility of consciousness in a physical universe. We get to watch. We get to wonder. And sometimes, with enough patience and careful thought, we get to understand.